Um, Good afternoon, all of you. I am resuming the YouTube videos again. Okay, so after a significant gap, we are back to the YouTube videos. Now, here, one important change is going to happen. That is, from this video onwards, the homework will be in the form of a PDF, which will be attached to the video. So in the description box below, you will see that there is a link, and the link is for a PDF which contains the homework which is related to this video. Now, in this video, I am going to basically concentrate on two topics. One is the concept of sin I by sin R, like how sin I by sin R remains constant even though I and R can change. So when a ray of light is entering one medium from another, like the values of I and R can vary, but sin I by sin R cannot vary because that is a refractive index relative to the two mediums, which has to be a constant. The other thing is that I would just like to quickly do a recap of the various sign conventions related to lenses. So these are the two things that I will speak about in this video. The homework, like I said, I will not write on the board. The homework is in the form of a PDF, the link to which is given in the description box below. You can try that after this you have watched this particular session. Okay, now I wanted to, like I said, discuss two things in this session. The first of them is on display right now. I wanted to discuss about the fact that sin I by sin R remains a constant when a ray of light goes from one medium to another. Sin I by sin R remains a constant even though I and R can change, but sin I by sin R remains a constant. So I wanted to start the discussion with that. So suppose you have a situation of refraction. Now this is the denser medium, this is the rarer medium, okay? This is the denser medium, this is the rarer medium, and this is the angle of incidence. Angle of incidence is 45 degree, and this is the angle of refraction 90 degree, right? So this is a denser medium, so angle of incidence is 45 degree. This is a rarer medium, angle of refraction is 90 degree. Now for this two pair of media, if I do sin I, okay, now one important thing is that by and large in every situation of refraction, we are always interested in finding the refractive index of the denser medium relative to the rarer medium. Virtually in all situations of refraction, that is what we want to do. We want to find the refractive index of the denser medium relative to the rarer medium. That's what we want to do. So over here, if you do sin r by sin I, so that will give you the refractive index of the denser medium with respect to the rarer medium. So this is going to be sin 90 by sin 45, so that is equal to root 2, right? So the refractive index of the denser medium, this one with respect to the rarer medium, will be sin r by sin I, sin 90 by sin 45, that is root 2. Remember, we usually want the refractive index of the denser with respect to the rarer. That is what we usually want. So whenever you want refractive index of a particular medium with respect to the other medium, it is always sine of the angle of the medium whose refractive index you want, that has to be in the numerator, and the sine of the angle in the other medium has to be in the numerator. That is what we generally do. So basically this is, you can say, Ri denser with respect to rarer, right? This sin r by sin I is denser with respect to rarer. Now let's go to diagram number 2. So here if you do sin r by sin I, it will be sin 45 degree by sin 30, and that is also coming equal to root 2, right? It is also root 2. Sin 45 by sin 30 is again root 2. You all know, all of you know very well how to calculate sin 45, sin 30. I mean, this is not a forum where we can stop and suddenly discuss what is sin 45, sin 30. You all have that basic knowledge of trigonometry. So sin 45 by sin 30 is again root 2. So you see what's happening is that when the angle of incidence is 45, angle of refraction is 90, the refractive index is root 2. When the angle of incidence comes down from 45 to 30, the angle of refraction comes down from 90 to 45, the refractive index is still root 2. So the refractive index is a fundamental property of this pair of media. So you can ask me a question that is there nothing that can alter the refractive index? Well, maybe physical conditions like temperature, maybe, and of course the wavelength of the light which you are using, right? So we will of course assume that temperature is constant for that particular discussion, and we will assume that we are operating with a particular light of a particular wavelength. So we will not tamper with those two informations. So we can safely say that root 2 and root 2 in both the cases is justified. For a given pair of media, the refractive index cannot change. So the refractive index of denser medium with respect to rarer is root 2. Now look at the third diagram. Now I was telling you that the angle of incidence in the first diagram is 45. In the second diagram it has come down to 30. The angle of refraction in the first diagram is 90. In the second diagram it has come down to 45. So the angle of incidence is coming down, the angle of refraction is coming down. So if you keep on bringing it down, so what is a rock bottom scenario? Both will become 0. That is called normal incidence, right? Both angle of incidence and angle of refraction will become 0. That is called normal incidence. You know that normal incidence is associated with the situation where there is no refraction at all. Okay, now this is very interesting. When you have normal incidence, can you do sin r by sin I? Can you do sin 0 by sin 0? Doesn't make sense. So please remember that sin I by sin r, or whatever, sine of the, the second angle with respect to the sine of the first angle, that is what we normally do, right? That is how we normally operate. We always do sine of the so basically the point is that when you are doing sin I by sin r, or maybe in these two diagrams we are doing sin r by sin I, whatever we are doing, it is when refraction is actually happening. The refraction is actually happening. Actually there is refraction over here. Actually there is refraction over here, correct? But here, is there any refraction? No, it is normal incidence. There is no refraction. So because there is no refraction, the Snell's law is not applicable here. it is not applicable, right? So mathematically also it is improbable, because you are getting sine 0 by sine 0, which is ridiculous, right? Sine 0 by sine 0 is what? 0 by 0. That nobody can determine. You cannot calculate 0 by 0. So mathematically also it is improbable, but physically, why is it improbable? Or rather, why it is not appropriate? Because there is no refraction at all. So you cannot use sin r by sin I over here. You cannot use the formula sin r by sin I, because there is no refraction at all. There has to be refraction, then only you can use it, correct? So what is the summary of the discussion? In diagram number 1, angular incidence, angular refraction both are very high, but refractive index is √2. In diagram number 2, angular incidence, angular refraction have come down, but refractive index is still √2. In the third diagram, angular incidence, angular refraction, both are 0. That means there is no refraction, so you cannot apply sin r by sin I. So there is no question of finding refractive index by this formula. So the refractive index is √2, and it will be √2 irrespective of whatever combination of I and R you use. Only there must be some refraction. If there is no refraction at all, for whatever reason, you cannot use the formula sin I by sin R or sin R by sin I, depending on which one you want to use. So this is the first thing I wanted to discuss in this video. Now let's move on to the second thing. Okay, so let's discuss convex lens. Convex lens, typically the object distance we take it as negative, the image distance we take it as positive. Magnification is V by U, so obviously magnification is negative. Magnification negative means that it is a real and inverted image. Now, what we will do is, the focal length of a convex lens is positive. Now, what we will do is that we will say like this, that suppose the magnitude of the object distance, like don't worry about negative, the magnitude, so I write like this modulus. Suppose it is between infinity and 2f. Suppose the object distance is between infinity and 2f. So the magnification will be between 0 to 1. Again I am putting magnitude, like this vertical bar means magnitude, means I am not bothered about the sign. So you know that when the object is very far away, when the object is at infinity, that time the magnification is 0, it's reduced to a point. And when the object is at center of curvature, then the magnification is 1. So when the object distance varies from 2f to infinity, the magnification varies from 0 to 1. Secondly, when the object distance varies from f to 2f, so the object distance will lie between f and 2f, then the magnification will lie between 1 to infinity, the magnitude of magnification. So you know that when the object is located at 2f, the magnification is 1, and when the object is located at the focal length, then the magnification theoretically is infinity. So this is the first detailing of magnification of a convex lens. The second detailing is that the magnification is V by U, but this time the object and image distance both are negative, right? So the magnification is positive. So here what happens is the object distance is between the focal length and 0. So the object will be between the focus and the optical center. So the object distance will be between the focal length and 0. So the magnification in this case in this case, the magnification will be varying from 1 to infinity. So suppose you have just crossed the focus. Let us say that you have just crossed the focus. So and then you are slowly coming closer and closer to the optical center. So as you come closer to the optical center, the magnification will be very high. And when you are very near to the focus, but just you have crossed the focus, and going towards optical center, that time the magnification, so I think I should use this magnitude sign. The magnification will be just more than 1. It will be just more than 1. And like I said, if you keep going closer to the optical center, the magnification will also keep going towards infinity. So these are the two diagrams for convex lens and for concave lens. So U is negative, V is negative, F is negative, magnification is always positive. Now regarding the magnification, the object distance you can keep it anything from 0 to infinity. If you keep the object distance at infinity, then the magnification will be 0. If you keep the object distance anything from 0 to infinity, the magnification will be less than 1. So it is always a diminished image. So these are the three possibilities of magnification for convex and concave lenses. So I'll just quickly summarize the discussion. For a convex lens, U is negative, V is positive, magnification will be negative. So if the object distance is between 2f and infinity, the magnification will be between 0 and 1. If the object distance is between focus and center of curvature, the magnification will be between 1 to infinity. Secondly, if the object and image distance both are negative, that means the magnification is positive. So that means the object distance is between focal length and 0. So magnification will be between 1 to infinity. That means if you just cross the focus, the magnification will be 1. And after that, the magnification will go on increasing as you approach the optical center. The magnification will go up to infinity. And in case of a concave lens, focal length is negative, U negative, V negative. So magnification is always positive. So as the object distance varies from 0 to infinity, the magnification will vary from 0 to 1. So when the object distance is infinity, magnification will be 0. Otherwise, the magnification will always be less than 1. So that completes this entire session of light. And after watching this, please try the homework. The link to the homework PDF is given in the description box below. And just send me your answers. There's no need to show the working, right? So that will be all. I'll end the session. Bye all.